Alright, so what we want to do here is take a look at your homework problems and show you how I would have worked them so that you can have a look before you have this stuff show up on a test. And so we're dealing with our decomposition of sulfuryl chloride, and the first thing they want to know is that what the pressure in atmosphere would be inside this container if we had no dissociation of the sulfuryl chloride. And what they tell me is that I have 3.509 grams of it in 1 liter at 375 Kelvin. And so this is just going to be a simple application of the Pivnert equation. And so we want to solve for pressure. So P equals nRT divided by V, which our moles in this case can be found from the mass that they give me, 3.509 grams. And the molar mass of sulfuryl chloride, if you add it up, is about 135 grams per mole. R in this case, since most of the rest of the problem is going to deal in atmospheres, I'm going to use the R for atmospheres. So 0.0821 liter atmosphere per mole Kelvin. And we're going to be operating at a temperature of 375 Kelvin in a volume of 1 liter, so that the pressure, if all of this remained as sulfuryl chloride, if we run that through the calculator, you'll see it 0.800 atmospheres. So part A is pretty simple. Just apply your Pivnert for your basic gas law equation. Part B then wants to know what would be the total pressure, or what would be the pressure of each of the gases at equilibrium if the total pressure happens to equal 1.43 atmospheres. Now we can make an ice table here if we want to, but we don't have any Kp value. It's not given to us. But because they gave us the total pressure, we can work around this. So if I were to make my ice diagram for SOCl2, sulfuryl chloride, on down the line, we could see that we know from part A that this is 0.8, and initially this is 0, this is 0. The change then, this is going to drop by x, and because these have coefficients of 1, they're also going to go up by x, both of them. And so at equilibrium, sulfuryl chloride is 0.8 minus x. This SO2 is x, and the chlorine gas is x. Notice I cannot make any assumptions or eliminate any values of x for the sulfuryl chloride because I have no idea what Kp is. I don't know whether it's big or small, so I can't apply the approximations. But what I can do is take a look at what's going on at equilibrium. At equilibrium, I know the total pressure is equal to 1.43 atmospheres. It also has to be equal to the pressure of the sulfuryl chloride plus the pressure of the sulfur dioxide plus the pressure of the Cl2 gas. So now I can just sub these things in. I know sulfuryl chloride is 0.8 minus x. I know the sulfur dioxide is x, as is the Cl2. So now I just simplify. If I have 0.8 minus x plus x plus x, I can see that one of these x's, pluses and minuses, will kill each other out. And 1.43 atmospheres then is equal to 0.8 plus x. And solving for x will tell me that value is going to be 0.63. And x in this case is equal to the pressure of SO2 and the pressure of Cl2 both. They're both equal to the same amount. So then the pressure of the sulfuryl chloride, we just need to come back and apply our 0.8 minus x, because that's what we said sulfuryl chloride is. So it's going to be 0.8 minus 0.63 atmospheres, so 0.17 atm. And so that's part B. These two are both equal to 0.63, and the sulfuryl chloride is equal to 0.17. Part C then wants us to write the value for the equilibrium constant for the decomposition of sulfuryl chloride. Then it says calculate the value of the constant you've given and specify units. Now notice this question is from 1983. This is an old school question. They used to actually record units for K values, but you guys know from what we talked about, modern convention says no units. We make everything relative to standard values. So if I divide everything by 1 atmosphere, I'll have no units. So this is an old question. They expected a different answer, but we're going to go with the modern answer. And so our value for Kp would be easiest since we already have pressure data. So Kp for this then would be the pressure of sulfur dioxide times the pressure of chlorine gas divided by the pressure of sulfuryl chloride, all to the power of 1 because all coefficients in the balanced chemical equation are 1. And so then calculating the value of that would just say that we have 0.63 for the pressure of SO2, 0.63 for the pressure of Cl2, and 0.17 for the pressure of the sulfuryl chloride, and all that together yields me a Kp of about 2.64. And again, no units. We don't use units on K values. Alright, part D then says, if the temperature were raised to 500 Kelvin, what effect would this have on the equilibrium constant? Explain briefly. Well, if we read through the information they told me up here at the top, one thing stands out. The fact that the reaction is endothermic. And we have an idea for what happens to endothermic reactions when we have heat. So because the reaction is endothermic, that means heat is a reactant. And so if we add reactants, then we cause products to form. And if more products form, then Kp will increase. So essentially we're just applying Le Chatelier's principle. If we think of heat as a reactant, we add more heat, moving up to 500 from 375. Then if this goes up, the products go up to relieve the stress in the system. And so since heat does not appear in the equilibrium constant, it will cause these two values to go up and this one to go down, which results in a larger value of K. And that is all it takes to answer the question from 1983.